doing getting into this chapter 8? All right, we've been into chapter 8. I mean, we're getting into the vibrational motion. So I love this stuff. This stuff to me is so cool. I do a lot of vibrational spectroscopy, so IR spectroscopy in my research. So I love getting into this stuff. So let's do it. So up to now, we haven't really treated the potential energy in a very realistic sense as far as our potential energy operator and our Hamiltonian. We've given it cases where we've called it some constant V. We've given it cases where we've called it zero, where we've called it infinite. But now we're going to approach a potential energy operator using something borrowed from classical mechanics, which is Hooke's law. Okay, so a particle undergoes harmonic motion if it experiences a Hooke's law restoring force. Okay, and the idea behind that is to imagine we have two masses on a spring. All right. And so this particle, or these particles, if you will undergo harmonic motion if they oscillate back and forth on this spring, and their potential energy is described by the following curve. Okay, so we call here this x. We're going to really be calling x displacement. So that's important to know. So we've, in this case, x, it's really referring to as the total distance this thing has displaced. Okay, so this might be one level of displacement, right? Up at the higher end of the curve. But, down here at the lower end of the potential energy curve, we might have a lot less displacement. Okay. So what we have, so this Hooke's law restoring force is given by the following: force, right? Okay, equals negative kf times x, where kf is our force constant in terms of newtons per meter. And of course, then displacement will have units of meters. So that gives us the proper units of force in newtons. Okay. We also recall from Newton's laws, force equals dv by dx, negative dv by dx, okay, where that's potential energy versus change in position, okay? And so if we do a quick little divide and conquer situation here, where I'm going to multiply dx over to this side, and I've got negative dv on this side, okay? And if I integrate both sides, then, and of course recognizing that f is kf times x, right? So that becomes integral of negative kf times x dx, all right? And then, of course, the integral of dv just simply equals v. So now when we integrate this thing, this is where we get the 1/2, so negative and negative signs cancel. This is where we get the 1/2 kf times x squared. And you can see right here, so now that's going to become our potential energy operator, 1/2 times kf x squared. All right. And so now, if we consider also our boundary condition, okay, one of the boundary conditions, we know that psi has to equal 0 when x equals plus or minus infinity. So as given right here. And so what that means is our oscillator can't, be displaced by an infinitely large distance, right? We are going to build in for the fact that this thing can only oscillate or only be displaced by a finite amount. Okay, so that's where we'll say its potential energy will tend to infinity as we go up and up and up. All right. And so now if I build up the Schrodinger equation here, you all know how we do this by now. Look, we've got our kinetic energy term, okay? So I'll just say Ke, right? Where we know that's the negative h bar squared divided by 2m times second derivative of psi. And then now we can build in this, what I'll say, Pe, our potential energy term, using Hooke's law for harmonic motion.